Okay, let's start. Thank you, Kami. This session is for how to generate the power model for EAS and IPA without talking to a hardware engineer. So we wanted to figure out how to use a simple method to generate the power model for the EAS and IPA. Because in tomorrow there have one session is duplicate session, but I will to speak in Mandarin. So if you have something interesting to discuss in Chinese language, you can attend tomorrow's meeting as well. So this presentation is delivered by my leader, Daniel Thompson, and me. We co-work for this slide, especially for the IPA. This part should be credited to Daniel because he introduced a very simple method for generating the power data. So later we will can see how to do that. So let's start. The agenda is that we will give very brief introduction for the background, why we need to need to generate the power data, power modeling for the EAS and IPA, and then we will to review the low power states, because for the operating point it's very straightforward. You just set the CPU to a specific operating point, then you can measure the power data. But the low power mode, it will be quite specific for the CPU's variants. So you should to get to know where for the CPU's low power states for the ARM CPU. Then we will to introduce the method to measurement the power data on the high key. Then we will to generate the power model, and finally we will to get some conclusion after we do some profiling on the high key board. So the background is generating platform-specific parameters for power models are a prerequisite for deploying EAS and IPA. So if we think, go back to review the HMP or the SIMO governors, we can get to know if we want to enable some software feature, or just to enable the configuration in kernel and to use it. But for EAS and IPA, it's quite different. You must first need to generate the power model on your platform, on your specific SoC, because the SoC silicon may have quite different the process. So you need to generate the power model data to reflect the real characters for your SoC. So software engineer needs these parameters to work on these features. And there have another thing is that gaining assistance from the hardware engineer is difficult. For example, if you work for a silicon company, then if they have a silicon engineer, they maybe can work with the bare metal code environment and to generate the power data. But how to convert the power data to the power modeling parameters, they don't have the knowledge. And also for the software engineer, if you want to do furthermore tuning and you want to refine that, I think that this you cannot get help, less help from the hardware engineer. You must to be aware as a software engineer to do this. And especially now in the Linux kernel, our SoC community, we also, because we also want to use some simple way can let the software engineer have no difficulty to generate these power modeling parameters. So this is why we think that it's possible to generate acceptable models using simple tools. Maybe perhaps there have some, the power model parameters is not optimal. So today we will only focus on the CPU, this part, but there also have the GPU or the DDR, this part we don't talk about in today. So here I have one flow. We can see if we want to use the enable EAS and IPA, the first step we need to do the power modeling and generate the power modeling data and pass to the EAS and IPA to enable it. And then after enable it, we need to do the profiling on the EAS and IPA. So, but this is not finished. This is just iteration for the later, so you optimize, or you should to confirm if your generate power data is correct or not. For example, it's the first time when I generated the power data on high key for EAS, I found maybe there have some mistake for that. So need to adjust that and go back to input the parameters again and use the new updated the power modeling and to do more profiling. There have another thing that because now EAS and IPA is ongoing for the upstreaming and for the developing, so there maybe have some space we can to improve and to optimize. So that's why after we profiling, we also can to go back to check the EAS or the IPA's algorithm itself can be optimized or not. So let's review the no power states. So here is the, because the high key use the CA53, the CPU, so we just focus on this kind of CPU. So for the CPU, there have three kinds of states. The first one is the CPU P state. That means the CPU is running at one specific operating point. And for the WFI state, that means the CPU have running, its power domain is on, but its internal clock is gating. So that means we can use this way to reduce the dynamic power. And for the CPU off, that means the CPU, the power domain to this CPU has been disabled and the clock for this CPU has been removed as well. So we can see for the CPU P state, there have the clock in, this single indicate that there have the clock is enabled for this CPU. And there have a PD CPU 0, that indicates that for the CPU 0, its power domain has been enabled. So this is a very normal state. It means that the CPU has been running in a specific state. So when the CPU executes the instruction WFI, that means that if we see the outside from the CPU, the clock source also has been enabled, and the power domain CPU 0 also has been enabled. That means the power controller in SoC don't do anything for this CPU, but the CPU run into the WFI state. That means in the CPU itself, it have the internal clock gating. So use this way, the CPU can reduce the dynamic power. But they still have the static leakage because the CPU has been powered on. So we can say for the CPU off, that means that they have the outside power controller in the SoC. It will to power off the power domain for this CPU. It also will to disable the clock for this CPU. So that means whatever neither the dynamic power or the static leakage, both of them has been removed from the CPU side. So let's go to furthermore is for the class level. So for the class level, actually, usually they have three states. For the P state means that the class level is powered on and has been clock enabled. They have very special state means that the class level cluster L2 retention state. In this state means that the L2 cache RAM is run into the retention state. But this state, usually we cannot very easily to use it because, for example, there have two clusters. If one cluster run into L2 retention state, there have another cluster. The cluster cannot do the cache concurrency with this cluster. So there we have the stale data in this L2 cluster's L2 cache. So when this cluster has been wake up and returned back, it will have the stale data. So usually if they have two clusters, we don't use the cluster L2 retention in this state. But if in system there only have one cluster, we can use it because we can use it to optimize the performance for the CPU idle latency, because we don't need to flash L2 cache every time when the cluster runs into the no power state. The third one is the cluster off. This means that the cluster has been totally be powered off. Yeah.
The middle level, the L2 retention, is this just happened on specific SOC implementation method, or is the common problem for all the Windows product?
Okay, I think this should be ARM to answer this question, but from a current situation is ARM have provided this state to SOC vendors, but also need the SOC vendors to implement this state in their own SOC. So means that some SOC vendors don't enable this state, but some SOC vendors can enable this. This is decided by themselves, by SOC vendors themselves.
Okay, understand, thanks.
So we can see this for class level state. We can see if there have, in the cluster, there have 4 CPU. If all the 4 CPU has been powered off, everyone by individually. But we can see in class level, the power domain can be powered on, and the L2 cache, the power domain also has been powered on. So in the class level, its logic also has been enabled, and there have the dynamic power and the stack leakage in this case. Here is the L2 retention state. That means that for the class level's power domain has been powered off, and the class level have also has been disabled the clock, but because the L2 cache, they wanted to run into the retention state, so it also still will be keep the power domain on this L2 cache RAM. So this is the L2 retention state. For the totally power off state means that for the class level, the power domain totally been removed, and the class level have no static leakage anymore. So if we want to look at the power states corresponding Linux kernel, we can see for the P state, there have the CPU P state and the class level state. Usually in Linux kernel, for example, for the CPU framework, we don't distinguish the CPU levels P state and the class levels P state. We just think it's the same one, and we are to change the frequency at the same time. But this is quite different from the EAS power modeling, because for EAS power modeling, we need to distinguish the CPU level and the class levels power parameter. So for the C state, so usually we will to use the CPU idle framework to manage these idle states. So there we will to register into the CPU idle framework for the CPU levels power state, for example, for the WFI and the CPU off. And we also can register the L2 retention state or the cluster off state. But for high K, in this case, we just register 3 states for the idle state, the WFI, CPU off, and the cluster off. We don't enable the retention state. So measurement on the high key. So This is just we just want to demonstrate how we can use a pretty simple method to measure data on SOC. So on the high key, we can review the PMIX hierarchy. Is the right is the SOC for the high 6220, this SOC. But there it has the power SNAND is the ACPU, so it's the CPU part. Then in the PMIC is the also is the Hasnikan's one PMIC. So there it will to output many bucks or LDOs to power supply the SOC. But there it will to have the dedicated buck one. It will to output to only to provide the power supply to the CPU part. This is a power SNAND. But the question is on high key the board design there they have not to leave the measure point for the buck one. So if they have so the buck one is an ideal measurement point, but the hardware design doesn't encourage measurement here. So we go back to use the outside from the PMIC, select the CPU's nearest measurement point. So we use this resistor to measure the power. So we replace the resistor as a 33 mini-ohms resistor. So we can use this resistor with arms energy probe to measure the power data. Also, for the arm energy probe, we also can use some Linux program to capture the power data. So we can capture the power data on the PC side. So that means, for example, now ARM have developed for the NISA framework. So you can use the NISA framework to capture the power data and also run the test case in one time. So this is why we can select the ARM energy probe here. So methodology for the power management is we just use one single CPU to measure the power. Because maybe they have quite different the measure method, because sometimes we can use the Linux kernel, very simple kernel, or we can use the U-boot, or we can use bare metal code. But for this case, we just use the ARM transformer to perform system suspend. So we use the ARM transformer to force the cluster and the CPU 0 to enter specific C state and P state. Here I have one flow is that we will in next page we are to present how we can first to hot plug off all the other CPUs, and we only to use CPU 0 to measure the data. Here I have another one important thing is that when we measure the power data, we need to base on the different operating point. The reason is that every operating point, they have different voltage level. So eventually, actually, we should to select the voltage level, and we base on this specific voltage level to measure the different idle state and the P state. So there have one case is we need to use the joint stone to generate 100% CPU utilization for CPU P state, so we can get the CPU P state, the power data. So for set up the power state, we use the method is, first thing is we should to set the CPU frequency to a specific operating point, so we can set the specific voltage. Then we manually need to hot plug all the secondary CPUs from the system. So there we only have one CPU, is CPU 0 in the system. So we can use the software flow, like the system suspend, to let the CPU 0 to run into the low power state. But for the CPU 0's low power state, we can hack trusted firmware, so we can select the specific hardware idle state. So for example, we can hack let the CPU just run into the power off state, or we can hack the flow to let the class level to be powered off, or we can let the system run into the real suspended state. So use this way, we can get different power data for different idle states. So this is a method. So finally, we can get one power data table. It's like this way. We can set the operating point to 208 megahertz, and its voltage is 1.04 volts. And the third column, this is the class power off state. So that means the two cluster has been powered off. But we can see there the class level has been powered off, but we can, as expected, actually I want to get the exactly same the power data at here, because that means that all the cluster has been powered off. Even the voltage is different, but it will not introduce any different power data, because internally in the SoC, the two clusters has been powered off. So that means that two clusters have no any static leakage and dynamic power. So whatever the outside, the voltage has been changed, but internally they will not introduce any difference. But from the measurement, we can get to know actually the baseline has been changed according to different the voltage level. So actually, I inquired this question with HiSemicon as well. So they give some question that maybe they have some logic have not been really be part of. So introduce some different here. For the class level P state means that all the CPUs has been powered off, but we have one class level has been powered on. So for the class level, its clock and its power domain are enabled. For CPU WFI state means that in one cluster, the cluster is being enabled, and the one CPU also run into the WFI state. So in this state, the dynamic power has been removed, but there have the static leakage you can get too low for this CPU. So for CPU P state is that we run the dry stone benchmark on this CPU. That is, this CPU run 100% utilization. So we can get the power data for this CPU. So this is a table. So next, we will to use, based on this table, to generate the power data for EAS and for IPA. So here is just a quite quick review for EAS energy model. For EAS energy model, there have quite important thing to be aware is that when you do the energy model, you not only for this CPU, you also need to calculate for class level. So this is quite different thing sometimes from some guys the understanding. So it includes the CPU's level. For in the cluster, there have multiple CPUs, so you should to calculate all the CPUs in these clusters power energy. And also you should to calculate the class levels, the energy. So for the CPU level, we can see it have the idle state, C state, and it has a P state. And for the class level, it also have different P state and the C state. So this is the basic concept is here. Before we go back to the power model, here I have one thing to explain is that for the CPU's capacity, we should to normalize the CPU capacity is normalize the CPU capacity is a ratio value. The ratio value between actual performance of the CPU and the maximum performance of the CPU in the system. So the maximum performance of the CPU may be is not maybe is the same one CPU kind of your measurement of the CPU. So such like in the big little system, the maximum performance CPU maybe is a big CPU with the maximum operating point. And we need to compare with the little CPU run at a specific operating point, get the performance value, and compare the big CPU's maximum operating point. So this way we can get a range. Then we need to convert this range into the from the 0 to 1024. If you are running on the big little system, so you should to use the benchmark to do just like this way. But if we, for example, for the high key, it's SMP, so all the CPUs are the same architecture. So we actually don't need to use the, it's not, we can also directly to convert the frequency operating point to a range from the 0 to 1024. So this is why we have doing on the high key is we just to convert the frequency this range to the capacity this range from the 0 to 1024. So the basic method to calculate for power data is quite simple. We want to get the CPU, for example, we want to get one CPU's operating point, the power data. The first thing we get the power data is the CPU's run at a specific operating point. For example, 729 megahertz. But when we measure this power data, actually it includes the class level's power data as well. So if we want just to get the CPU level's power data, we need to remove minus the class level's power consumption. So finally, we can get the CPU this level's operating point, the power consumption. So this is all the data's calculation based on this discrement the calculation. So for CPU C state, we can see for the class levels, power on state means that the class level has been enabled, but there have all the CPU has been powered off. For the CPU WFI, this column means that there have one CPU has been run into WFI state. So we use the CPU WFI power data to minus the class power on state. Then we can get to know the CPU's WFI power data. But you can see here is a very interesting thing is that for WFI state, actually it's initially is the static leakage. So, but the static leakage actually is impacted by the voltage. So we cannot get a very unified data here. So for example, for the high K, it's the highest operating point. The voltage has been increased very sharply. So we can say at the 1.2 gigahertz, the static leakage is quite high than the normal average value. So how we can select a value can be accepted by the energy power modeling And here, I just to select the middle value. I think that is the most often we can use this value. So I just select this one. But in the energy model, the table, we need to select one will be enough. But it cannot to reflect all the voltage levels, the power data is here. So here, have one thing we should to take care is for the idle state. Actually, when we pass to the color framework, there have active idle state. Later we will to explain what's the active idle state. But here we just take it as the WFI state. So we can see for WFI state and active idle state, the power data is 15. But for CPU power off, we just think it has been really be power removed. So its power data is 0. And for the class level, power off. That means all the whole cluster has been powered off. So for the CPU level, also have no power data anymore. So we also set the value is 0. For CPU P state is quite straightforward. Is when we run a CPU with benchmark, then we can get the power data is here. And for the second column, that means that the CPU has been powered off, but the cluster is powered on. So we just use the third column to describe the second column, then we can get the power data. So we can directly match to the CPU's P state table. So here I have one. Actually, when I read the EAS, the patches, here is also one thing I'm a little confused. I take some time to understand is the active idle state. So the question is, actually, there have a software behavior is, we can think that there have 4 CPU in the cluster. Every CPU is not work anymore. So this is software. If we think this as the software's view or perspective, but actually for the CPU, the hardware, actually they can have different power states. Maybe the CPU has been run into the WFI state, or maybe the CPU have been totally be powered off. So here have one state, it just to indicate that it's an active idle state. So that means that if we think from the class level, the cluster actually has not been powered off. But for the CPU level, actually, if we think that there have no any software run on these CPUs, but actually the CPU maybe has all have been powered off, or has some CPU have run into WFI state. So here looks like a mixture power state. So the question is, this state is a P state or C state. The difference is, if we think it's a P state, so actually it's one single state. But if we take it as a P state, so actually we should to think about what's the current its voltage. So the different voltage may introduce quite different the power data for this state. So we can see next page. When we generated the power data for class levels power state, we need to generate the active idle state. So we can see, if we think that there have a low CPU is running, but for this case, actually the class level actually is being powered on, and the clock also has been provided for this cluster. So for different operating points, the power data for the class level actually is quite different. So we can see for 208 megahertz, the power data is 16 milliwatts. And for the 1.2 gigahertz, actually its power data is 112 milliwatts. So it's quite different. But actually, when we need to create the EAS power model and pass this parameter to the color, we need to pass one parameter. So we cannot use this parameter to reflect this difference. So finally, I selected also the middle value of the 47 as the value to select for the active idle state, WFI state, or CPU off state. So here we can take as this is class level idle state. The last one is the cluster off state. That means the whole cluster has been power off. So the whole cluster will have no power consumption anymore. So its value is 0. But for the active idle state means that actually is estimated idle state. So we just select 47. And for double state means that for the CPU level, all the CPU has been run into the WFI state. And for the CPU off state means that all the CPU have been powered off. But this value also will to reflect the class levels power state, class levels idle state. So we also select the 47. So at the very beginning, I sent an email and confirm with Morten Ditterman. Here, actually, I have some idea in that. I'm not sure, but it looks like this state looks like we should to take it as the class levels P state, or for the active idle state. We don't it's more better looks like, but not take it as the idle state. So if we calculate this state as the P state, we can get to low calculate based on the operating point. So here I have a little question it here. Well, yeah. So for class level P state, actually is also very straightforward. We actually it's the same table with the previous class levels C state, but for the P state we can see every power data can have the corresponding operating point. So we can just to get the value and generate the table for the P state. So we just to use the class levels power on state to discrement the class levels power off power state. Then we can get to low the class levels P state power data. So finally, this is the table for the EAS power modeling the parameters. So for the EAS power modeling parameters, we can see they have class level and the CPU level. And for the class level, we need to set its C state and P state. So for the C state, the most thing now, they have the active idle states is special for the class level. But for the CPU level, they also have two tables. One is for the idle state and for the P state. So we just use, this is just parameters generated for the ES. So for this table, have any question? Okay, so let's go on to IPA power modeling. So for IPA power modeling, actually it's used different the power modeling method. Now we can there have some discussing to unify for the power modeling, but currently the IPA power modeling is used different. It will to distinguish the dynamic power coefficient and the static power. So we can see for the ES, the power parameter is based on the scenario you can measure. But for the IPA power modeling, it looks like when you measure the power data, but you should use some method to generate the coefficients and pass to color. So looks like it's currently is different method. For IPA power modeling, the global framework is they have the CMO driver. So CMO driver where to report the temperature, SOC temperature to the CMO framework. So CMO framework to get to know the temperature. If the temperature have reached to the tree point, it will to capture the SOC components, the power request. So, for example, there have the GPU, it will to use another driver, means DV cooling device. But for CPU part, we just use the CPU cooling device. So in the CPU cooling device, it will to calculate the requirement from the CPU part. What's the dynamic power it request, and what is the static leakage it requests. So after gather these two parts of the power data together and return back to IPA. So IPA is use its algorithm to calculate how much the power can grant to the CPU. So finally, it will to return in the 5 step. It will to update the allocated budget to the CPU part. So in the CPU cooling device, it will to use the power data to convert the real CPU P state can grant it to this CPU. So for the CMO framework, they use the power data. But in the CPU cooling device and the CPU framework, they need to convert the power data to a specific P state. So here is the different way. Is the general information is different from the EAS. So another thing is that the power modeling based on dynamic power and the static leakage. Now in the IPA, they don't distinguish for the class level and for the CPU level for the dynamic power. So you just need to pass one parameter to calculate the dynamic power. So it will not distinguish CPU level or CPU class level. But for the static leakage, there is a platform dependency code. So you can distinguish or you can don't distinguish. It's decided by your platform's driver code. For the temperature, actually, usually it will a lot to impact the dynamic power. It will to just to impact the static leakage. So when you calculate the power data, there will have some relationship between the static leakage with the temperature's difference. So here is the, we can see, here is the power model as the linear equation. First, we can see the IPA's power data can be calculated as the dynamic power plus the static leakage, static power. So for the dynamic power, its detailed equation is capacitance multiply frequency and multiply voltage square. So if we can see this equation, we can review this equation, we can get to know that the capacitance is a constant value because it really on the SOC's process. For the static power, actually it's not a constant value because it will be changed by the temperature, impacted by the temperature. But if we want to simplify this equation, because here I have some assumption is, the first thing is that if we do well for the temperature control for this SOC, for example, we use the Simon governor. Another thing is that so we can let the static power not to change too much. The second thing is that because the static power actually is a small part of the total power data. So at this way, we can simplify it as a linear equation. So, or we can apply the linear regression on the measured power data on it. So the equation can be simplified as the y equal m plus x plus b. So we can symbolize the m and b as the constant value. We can use the leanness, the functionality in most of the spreadsheet programs can do the calculation. Actually, this is Daniel introduced this methodology. Okay. Oh.
So here was that capacitance in the previous slide. This one is a constant, right?
Yes.
But it's a function of the C. Okay. So what's your purpose for the second one? You're trying to use a linear equation to approximate the power?
Yes, well, because now we measure the data is y and x, so we want to get to know what's the m and b. So,
M is the slope, right? B is the intercept.
Yes, yes.
What is x?
X is frequency multiplied voltage square. So voltage,
okay.
Frequency and voltage also we.
Oh, you just read that into a linear form.
Yeah, yes.
Okay, got it. Thank you.
So we measure the power data. So we review the class power in this column, and for the x is the frequency multiplied voltage square. So we can directly to generate the linear regression on the cluster power, so we can see it can match well with our measured power data. So we can see for the x, it's the voltage multiplied the frequency multiplied voltage square, and for the y-axis is the power data. So the blue point is our measured the data, and we apply the linear regression on this measured power data. Then we can get this linear line right here. So we can see that this linear regression can match well with our measured power data. So finally, we can get the intercept about 5 milliwatts, and we get the gradient, it equals our capacitance, this value 0.051. So for CPU level, we also can use the same method to apply for the CPU power data. Then we apply for the linear regression on the measured data. But here I have found one question is that the intercept is a negative value minus 27. So here is one thing is that not make sense is that means that the static leakage we can get a negative value, but we cannot to pass this negative value into the Nernst curve. It will introduce the error. So this is quite this is introduced by that the highest two operation point increased its power, their power very sharply. So that this gradients to get to know and intercept get the negative value. So how to resolve these issues? So here I have some potential solutions or options. The first thing is that if we cannot to have the negative stack power, because get state power cannot return negative number. But we can force the linear regression through 0 if we accept that this will be some flow in the model. So this means that we can totally ignore the static power. We just use the Dynamic coefficient to calculate. The second option is that we go back to capture the temperature, also capture the power data. Then we can generate the relationship between the temperature and the power data. So that means that maybe for 1.2 gigahertz or the highest operating point, they have heavily impaction on the temperature for the power data. So this way also can to check if we can generate more, make sense, the reasonable the power data or not. And the third one is that can we directly to use the EAS, the power model data, apply on the IPA. So use the EAS, the power model data. We don't need to generate the capacitance. We just to, based on the measured data, to get to know what's the power data for 1.2 gigahertz, something like this. But if, for this, currently our case is we don't do the third and the second and the third one, the option. We just simplify the power modeling. So we just use the linear regression through 0, this method. So when we use the linear regression through 0, we can see we can get the orange, this line. If we compare with the pink, this line, we can get to know actually it will to introduce more errors for the modeling. So, but if we compare, if we use the linear regression through 0, it will give him worst case error of about 10% if we compare with the real measured power data. So we think that it's not introduce very huge errors in here. So we use this way. So as the final calculation is that we use the class levels, CPU levels, the gradient, and add the class levels, the gradient of capacitance. Because for the class levels, we need to divide to every CPU's level. So finally, we need to divide 4. Then we get the 311, this value for the IPA, the dynamic coefficient. So this is a very simplistic power modeling. We don't take account for the static leakage. Here, have something think about this is because just now we have said that this is non-linear rated for the CPU power data. So the static power actually is potness. And update the value for class level capacity, which is now forced through 0 as well. There also have another thing is that error in the model can be tolerated in some use case. Dynamic power remains main contributor to the power consumption. Also because the PID controllers integral term will partly compensate for the temperature drift. So we also can rely on this to dismiss some errors in our modeling. So, okay. This page is that how to decide the sustainable power based on the operating point. Here is quite straightforward. Is when I set all the 8 CPU to 1.2 gigahertz and run the benchmark, we can see there have the power increase very sharp. But this is not. This is just impacted by the temperature increase. So finally, introduce the power will be increased very sharp. But for the CPU run at the 980 megahertz, we can see when all the CPU is running, actually the power data will to increase very slightly. So that means that the temperature impact on this state very slight. And for the CPU run at the 729 megahertz, the temperature doesn't increase. So its power consumption is less than the sustainable power. So we select the 980 megahertz as the sustainable power data. So finally we can get, here is the table. In this table, actually this data is calculated by the dynamic coefficient. Then we can get the corresponding operating point, the sustainable, the power data. So finally we select the 960 megahertz, the sustainable power data as the selection. So conclusion is IPA was very effective on high key even with the poor model. We compare with our previous stepwise governor, we can increase about 40% performance improvement. Here have one thing is that allow EAS model to be used for IPA, allows direct link between observed value to power model mode. Using EAS value directly to convenient for simple system, although it makes it impossible to exploit the model die temperature effects. Another thing is that maybe for more accurate the power modeling, maybe later we need to capture the temperature also alongside the power data. The next suggestion is that for currently the CPUs, for the CPU's power consumption, the data calculation, we don't consider if the CPU is run the utilization. So, for example, if there have 8 CPU, and if you calculate the CPU's power data in the IPA, it will be able to directly to calculate sync as the CPU running at the 100% utilization, right? Oh, sorry. Oh, use the global the utilization value, right? Oh yeah. So here I just think maybe later we can, if we integrate with EAS, we can use the scheduler, the utilization parameters to get more accumulate the.
Yeah. Maybe because the way this scheduler calculates utilization, it's a geometric series. It's got a decaying function. Yeah. While for thermal we tend to use the square window. Yeah. We tried using this. Yeah. Yeah. So we tried using the scheduler. Well, we compared the two signals, and we found that the square window is better for thermal purposes. So
you have finished the profiling for this, right?
Yeah, we did some sort of stuff last year, and we kind of, at that point, decided to kind of stick with the square window. In the future, we may revisit, but at this point, there was no good reason to change it.
Okay. Thanks. Yeah, so have finished. Yeah. So have any other questions? Yeah.
Well, then you need to run to the next session. It's next door if you're an employee. Thank you, bud.
Well, I was just wondering if you tried this methodology on a different platform just to kind of prove that the idea is generalizable. Have you tried a similar sort of way to build a power model for a platform other than the high key model?
What's a high key monitor?
Sorry, have you tried this on a different platform, the method to build the power model? Have you tried it on another platform?
You mean the other platform, right? No, haven't.
No.
Yeah, currently only have the high key board.
Okay. Well, I was curious how widely it applies, because if it does, it's really cool. It'll kind of be a big step forward in terms of building the power models for EAS and IPA. So.
Yeah.
also the question about the power model equation. The equation, yes, the equation has static power. So the static power sometimes is still, it may be the cluster part, or maybe some the other non-idle CPU part. So is that static power just, what do the details static power mean?
The static power means that we can understand as the frequency has been clock gating, or the clock has been gating for the logic, but they have the power on this logic, so it will have the static power leakage. That means that, for example, for the CPU, if it runs WFI, so it's clock gating, so they have low dynamic power.
Sometimes not only the leakage, I think when some of the CPU is maybe idle, but the cluster part is not idle. So
yeah.
In this status, all the exist power belong to the static power.
Yes. So this is why you can see we don't cannot measure the class levels static leakage. Why? Because for class level we have know the specific state to disable the clock for the cluster, right? But for example, some SoC vendors, they may have specific power state can measure like this way to disable the clock to the cluster level, but it will still to power on the cluster. So it can to calculate can measure the static power. But you can see it here. We cannot measure, so we need to try to use some formulation to calculate. So this is quite different. If you have the hardware support, you can measure. But if you haven't the hardware the solution, then you should to use some method to calculation.
Okay, thanks.
Could you move to the last page? Yeah. So what do you mean use CFS CPU utilization? This is the same like CPU load usage. So what's the difference?
From my understanding that currently is used the global, the static for the CPU's duty cycle to calculate. But for the CFS CPU utilization is very, very detailed, the parameter in the, for the every CPU's run queue. So it's different, yeah. But this looks like more accurate.
Okay. Okay, thank you.
Okay, have other questions? Okay, thanks you all coming. Thanks.